Right. So Emily, thanks very much for joining us. You're in Chicago, right?
Yes, I'm frozen Chicago, but I don't think we're getting too much sympathy for that these days.
And things are okay with COVID or not? Are you in lockdown?
We've been fairly fortunate, I think, compared to most other major cities. I'm actually out a little bit more in the suburbs anyway, so like not kind of in the heart of the congestion, so we're getting along.
I was looking at your books in the background. You've got all the classics. I see Alpha Data Science, BDA3, all the good ones. And so, did you grow up in Chicago, or did you?
Yeah, I've been here mostly my whole life, except for I was at UNC Chapel Hill for college, and definitely had the weather optimized those years to spend winter in North Carolina, summers in Chicago. If you can ever be a migratory species, I highly recommend it.
I was trying between Australia and Canada, and then COVID hit and closed all the borders. And so you study maths as an undergraduate. And were there any particular reasons sort of for that?
I think a couple of different reasons. The first is probably a little bit more of a cliche of just I'd always liked it in high school and junior high, always seen myself as a numbers person. But I think in that regard, I really got lucky because I think what we tend to see in our primary education is mathematics has very little bearing into what actual college and more theory-based mathematics is. And I just kind of happened to luck out, and that I ended up liking them both. And then also, as you mentioned, earned a degree in statistics. And I think that was kind of my attempt at just kind of marrying wow, I really love pure math. How do I apply all of these just concepts that really appeal to me and the stuff that seems really beautiful? And how do I get a job with that? And I think statistics then just really amazed me from my very first class, in that it was just amazing to me, this notion that we could use numbers to understand people and to understand the real world. And once again, I think I kind of lucked out, because the thing that first appealed to me about statistics was the idea that there was a subjective way to use numbers to get a lot more certainty. Turns out that's also very much not true. And I think causal inference is a really good example of that you're actually just opening yourself up to all sorts of other different dimensions of uncertainty. So got into the degrees on very false premises, but still happened to love where I ended up.
Were there any that's remarkable. Were there any teachers or professors that sort of stand out while you were at UNC? It sounds like you had some fairly important statistics courses, perhaps.
Yeah, so I think really the professors that stand out, as I think back, really on two dimensions. I think something that I value both in my own career and in my own learning journey and in the people I look up to are the ones that really had a sense of, even into the middle and the end of their careers, a sense of hunger and playfulness and just real passion for what they were doing. And that would come into class and be oh wow, I was pouring cereal or standing at the train station. And I was thinking about how this could be a mathematical model, and people that really truly embraced it. And it wasn't just perfunctory, I think were really inspiring and something that I kind of aspire to be in my own life. And then really on top of that, I think beyond professional success, I was lucky to be around some of the most incredibly kind, supportive, just wonderful human beings as professors who were just really willing to invest in their students, such as me. And I think obviously that also made a big difference and was a good reminder that there's a lot more to success just in technical skills.
Yeah, and I mean, that's one of the parts of R that I really like, actually. So, I mean, we were talking about the Alpha Data Science book in the background, right? But you I've never met Hadley Wickham, but you do feel as though he's supporting you. Well, I feel as though he's been supporting me in my R journey and things like that. Were you always into R, or did that come later? Or?
That actually came a lot later for me. One kind of fun fact depending on who you ask about UNC, is that we're probably within 5 or 10 miles from the SAS headquarters, which had the result that SAS like probably was giving us some money, and one way or another we ended up using a lot of SAS. And I really only lucked out in 1 or 2 classes in my career at UNC. I was had to use a little bit of R, but I would not say I was like good at it at all, mostly just very perfunctorily like stealing code from ISLR, trying to like get it to run on a different data set, Googling things that didn't work. But I was lucky enough to have one professor that made us do our homework in our Markdown, and just kind of the nugget that was possible to like integrate code and text together was really powerful and really interesting to me, even though I was probably not that great at it at the time. And carrying that forward into my career actually was probably one of the most like tiny, inconsequential, but game-changing things that happened.
There's so much there that I want to unpack, but I'll try and stick on the straight and narrow. You mentioned R Markdown, and you literally wrote the book about R Markdown. What was that sort of experience like? I've put the link in the chat for folks that aren't aware of this.
Well, I'll say 2 possibly contrasting things. That was it was an absolutely incredible experience. I was so lucky to get to engage and work with Yue and Christophe, the other 2 authors. However, if anyone does actually want to go pull all of the Git commit history from that repo, which, side note, fun API, fun data science project, you will see that I did actually join that project pretty late on, and definitely only like I can only take credit for a very, very small fraction. But no, it was like really an amazing experience seeing end-to-end the process of how a book gets published. And on top of that, I think just a great example, like reflecting on how that project worked versus how a traditional project work went. I found that very amusing too, from the standpoint of we were probably all in touch for many months on that without ever having a single meeting. Almost everything we talked about, either an email or GitHub issues or just pull request messages. And it's definitely, as I go back to my day-to-day work life, really put a whole new spin on the whole could have been an email philosophy.
Yeah, you should try academia. You're now a senior analytics manager at Capital One, and you've been there straight out of uni. And so you started as sort of a business analyst, you get promoted, senior business analyst. What were you sort of doing when you first came out of uni? I mean, without specific, broadly.
Yeah, so one really interesting aspect of my first job, and I could talk later more when we talk about careers about some of the pros and cons of this, is I wasn't a very like wide-ranging generalist role. So very data focused, very data driven, but doing everything from more inferential and descriptive statistics, understanding the current state of our business and our customers and their performance, more kind of exploratory analysis to generate new ideas, and then more of your traditional like predictive analytics, working with models, trying to figure out what's next, how we better, target different things that we want to do with our customers to achieve better business results. And I think it was a huge departure from school where it's like, I'm taking a survival analysis class right now. So I know that the kind of model I'm fitting is a survival analysis model for survival analysis data. It was kind of fun to be in the immersion of that, where you just had very like wide-ranging and somewhat unrelated problems flying at you, and kind of tracing back to like what general problems in your toolkit might be applicable here.
Yeah, it's such a difference when you start your first job. And then finally, in terms of this sort of background section, and then we'll turn to the causal inference aspect, you recently presented at RStudio Global. What was that like? I'll put the link in the chat for folks who want to watch that later.
Yeah, no, that was definitely a great experience. It was my 3rd time, I think, at RStudio Conf, and definitely, on one hand, missed out on a lot, not getting to see everyone, not being in person. But I think the virtual conference ecosystem that sprung up, and I think even like this forum's a fantastic example of that, is probably one of the things I'd regard as the most exciting and positive consequences of this strange world we've lived in. The fact that just you can share ideas with so many more people so much more expediently. I think it's pretty exciting. I know I definitely enjoyed being able to watch so many more talks than I could have at previous conferences because I didn't have to choose between tracks. It was just like, why not both? And later this afternoon, I'm headed over to a meetup in the UK. So that was definitely a lot of fun and one small silver lining of the world in which we love.
Yeah, I'm not sure how we're going to navigate the path back. Like it seems impossible to go back to the old way of doing things. The main reason for having you here was to talk through a incredible post that you wrote about causal inference from observational data, and I've just added that into the chat. At certain points, whether you want to share your screen to like sort of illustrate various things, or I might share my screen to illustrate various things, then feel free. You've got co-host privileges. Awesome. But for those of you in the audience, we're just going to largely just go through this post in order. I've actually been a big fan of yours for a long time now, and you're actually going to be presenting a package at the Toronto Workshop on Reproducibility in a couple of weeks called Convo. And so I was just shocked when I saw this post, and then there was another post about data sets, and you just got such a variety of expertise. It's remarkable. And in this post, you walk through some of the common ways that we can become comfortable with making causal claims, even when we only have observational data. And so there's a lot to unpack there for those folks who are unfamiliar with this language. Could you just sort of talk a little bit about this? What's the fundamental problem with causal inference?
Yeah, so I think the fundamental problem that we're always trying to solve is if I really want to know if doing something has any sort of effect, what the ideal way that I do it, like if I want to see if Rohan is a better or worse interviewer, whether he has his cup of coffee first or not, inspired by the mug you just picked up, ideally I'd get 2 Rohans, give one his coffee, not give it to the other one, even though that might not pass IRB because that's just cruel. And then I'd observe the different outcomes in those 2 settings for every exact same individual. But of course, can't do that in real life because we can observe the same outcome, both treated and untreated, for the same individual. So the best we can do is try to get some sort of proxy population and find ways that we can compare 2 similar groups and look at a treated group and an untreated group, instead of looking at those 2 outcomes at the individual level.
And so if we have such issues with like this observational data, then why don't we just do, RCTs, randomized controlled trials or A/B tests or experiments? Why don't we just run around doing that like all the time?
Yeah, no, it's a great question. And I think those types of methods have become profoundly popular in industry. I think if you just go on LinkedIn and search for job postings with A/B testing or experimentation, you will find so much out there. And it is really like fantastic that so many companies are in on that. But I think, unfortunately, that isn't always an option for a lot of different reasons. Kind of practically, a lot of these methods come from either epi or economics, where an econ, like maybe an economist doesn't have control over the minimum wage in different states. So we can't go randomly assigning that by himself, but he might still be interested in the effect. Or we also can run into ethical issues, but a common example there more from public health is I can't decide to randomize, tell some people to smoke and some people not to smoke, just to tell the effect of smoking on lung cancer. And even though those are examples from other fields, I think a lot of the same challenges also come and relate pretty closely to industry. We don't want to always give some customers an intentionally more negative customer experience than others and raise potential questions about unfairness. Sometimes tests can also just be really expensive to implement, like even to test 2 different user interfaces on a website, we're asking our tech teams then to go change button colors instead of doing what else they'd be doing. And I think a third set of problems is when we want to look at longer term effects. One kind of classic situation in which experimentation falls down is that there can be a short-term effect that dissipates over time. But if I want to know something about how does this affect my customers' like 5-year retention rate, I don't probably want to just like drop a test and then go for a very, very, very long coffee break just while I'm waiting for an answer.
Yeah, I think these are fantastic points. And so the final bit of terminology that we sort of need before we can dive into the different analytic approaches is the counterfactual. And so could you explain a little bit about what a counterfactual is and its role in all of this?
Yeah, so another like term that I've heard for the counterfactual that sometimes is maybe more intuitive to think of is the like but for. So you can kind of think of it as like, but for this thing happening, what would I have seen? So essentially in causal inference, we can think of that going back to the situation of not having two Rohans, is a counterfactual is kind of like the Rohan, but for his cup of coffee. And essentially all of the methods we're going to talk about today are different ways that we can never observe that counterfactual, but we can try to proxy it of this like hypothetical situation where everything in the world is the same, but I plucked away the treatment if you got it, or I imposed the treatment if you didn't.
I love that. When I'm teaching the pipe, I always try to not say pipe, and I try to say and then, or some words to that effect.
Oh, nice.
I sort of think that we should name these things sort of better. And the but for is certainly much better than calling it counterfactual. That's a great idea. So the first technique that you talk through in your post is stratification. And so did you want to talk a little bit about this and why you might want to use it?
Yeah, definitely. And if I look like I'm talking or doing something while I talk, I may actually pull up kind of my pictures here on the blog post just for a little more color to some of these methods. I think essentially, like, you can think of all of these methods, going back to our discussion of the counterfactual, as different ways to exploit naturally occurring variation in our data set when we like can't experiment in order to kind of like mimic that counterfactual. And essentially the first of these is something called stratification. And the kind of like bias that this is able to help mitigate is when we have groups in our population that are objectively similar between treatment and control, but may have occurred in different distributions. So an example I give in the post is, suppose I try to like test if a one-click instant checkout button on a website could like cause different behavior, cause different spend amounts, but maybe the Chrome users for some reason in my test saw that more often than the Mozilla users. And things like the browser someone uses can actually be correlated with other features about them and behavior. So this could actually have the impact of, if like Mozilla users tended to spend less anyway, biasing the outcome between those two groups. So in this case, something like stratification might heroically come in and try to salvage the results of a kind of botched experiment. And the way this method works is essentially you can just like bin or stratify your data into smaller groups that you can think of as actually being kind of more similar. Essentially, you're like kind of controlling for some of those differences, kind of just by like cutting them into smaller boxes. And within each box, you can assume that more of their covariates, more other types of their behavior are more similar. So in the browser example, we might calculate the treatment effect separately for the Chrome users and the Mozilla Firefox users. And then finally, as the last step, we could weight average those two treatment effects together to get back to the overall treatment effect.
I love that. And as you're sort of talking, I'm actually thinking in like R code or tidyverse code as to like how you could actually be coding this. It's such a lovely explanation. And I love the example as well. And the next sort of method that you then talk about is propensity score weighting, a fairly closely related approach. Did you want to talk a little bit about what this is and when we might use it?
Yeah, definitely. So I think to understand propensity score weighting, I think it's really helpful to understand where and when stratification can break down. You can imagine, like in that example, I just had like kind of one variable that was categorical, super easy to just spin those and go on my way. Now, suppose that I knew I had those kind of like similar groups of customers, some got the treatment, some didn't, but if they were actually different in distributions across many dimensions and many continuous dimensions, it starts to be really hard to do stratification, and we can run into a lot of the problems you associate, like the curse of dimensionality. So one thing we want to do instead is kind of like project all of those differences onto a like simpler plane that makes it easier to rebalance on. And that's kind of what brings us to propensity score methods. Essentially, how these methods work, and it's a really beautiful thing, but it's like a little bit unintuitive at first. So I'll try to like walk through this one a little more slowly. But and I'll kind of start off, I guess, kind of with the example here again, just to kind of make things a little more tangible. Suppose in this case, I wanted to text all my customers and see what's the effect of texting them on a promotion of them coming back to shop at my store again. And maybe I like text every single customer who I have their phone number. The only customers I could use then in my control group to compare against would be the customers whose phone number I didn't have. But you can assume there's probably some intrinsic difference between customers that were engaged enough to give me their phone number and customers who weren't. But I mean, those probably aren't completely unrelated groups, because maybe some just care more about their privacy, mix that box in the checkout flow, we're in a hurry. It's kind of random. But so the first thing we do in propensity score weighting is model and try to predict the likelihood of someone getting the treatment, which at first is weird, right? Because if you think about it, we know that. It's like, seems silly to like predict something we know and not try to predict the thing that we don't know, which is the treatment effect. But there's good reason for it. When we try to predict that likelihood of receiving the treatment, or in this case of having our phone number, we get a plot of kind of the distribution of those propensity scores that looks something like this, with the people who actually got the treatment skewing towards a higher likelihood of getting the treatment, and the people who didn't get the treatment skewing towards a lower likelihood of getting the treatment. But really crucially, you can see there's some overlap, there's some probability throughout this whole space of everybody like maybe looking a little bit like the treatment, even if it's unlikely. So what we can then do with these propensity scores is we can put more weight on observations that in the control group that look more like the treatment group. So observations down here that did in fact receive the control but look a lot like the treatment, we might want to weight really, really highly because we know those are more representative and more likely to be similar. And ultimately, maybe we could reweight our data so we get some distribution that looks a little bit more like the green dashed one and better mimics the treatment group in the likelihood of getting treatment, with the assumption, and there are like proofs behind some of this, that balances all relevant, important like covariates that affect the outcome under certain conditions. So then similarly, this is just showing the reweighting of the scores themselves, but then we can use those same weights to actually weight our outcomes. So then we can calculate the estimated effect on the treated, on the control, and find that difference to find the causal effect.
You do such a better job of explaining this than I ever do. That was incredible.
I doubt that. I spent a weekend prowling through your class notes very jealously. So,
and so we've been talking about propensity score weighting. Is there a difference with propensity score matching? Is it a similar idea?
It is a very similar idea. You calculate like the propensity scores in exactly the same way. There are just, I think, more like the matching part is where it gets a little trickier, and there are more subjective decisions in exact matching versus inexact matching, how much to weight, like closer neighbors, further neighbors, big bandwidths, narrow bandwidths. And honestly, it's not something that I've had a ton of experience with. In the post, I do link to one really interesting video by Gary King at Harvard, who talks about some of the, what he sees as some of the like shortcomings of propensity score matching. I think I do. I think it's in the related resources post actually. But yeah, very, very similar idea. And in some ways, like matching is almost a form of weighting in which you're only going to end up with like integer weights. So that's probably the cleanest tie between them.
Yeah, there's academic like academic talk bingo cards, and whenever somebody uses propensity score weighting or matching, it's always just brutally attacked. And I guess you've got a maths background, and so you probably come at these things a little bit more sensibly than some of us with an economics background, such as myself. Did you want to talk any more about propensity score weighting, or shall we move on?
I think that probably
That's it. Okay.
Mostly hits the highlights. Definitely happy at the end to take any questions if there are any on it.
My other and in terms of implementation, so we're using logistic regression mostly here because we have, is that correct?
Yeah, I mean, you can calculate the propensity score with, I have seen like other methods too, just even like random forest type estimators and others, but really like kind of the most classic example is definitely a logistic regression.
Yeah. It's the old joke about it's AI when you're raising funding, machine learning when you're hiring, and logistic regression when you're implementing. But
isn't it the truth? I'm so sorry. I'm afraid my microphone's probably getting a lot of noise from my computer fan just turned on. Let me try to switch microphones really fast. Okay, can you hear me?
Yeah, I've got you. Yeah.
Okay, awesome. Okay, I think hopefully it should be good. Hopefully that sounds a little better now.
Okay. It's not a problem for me. I can hear you perfectly.
Okay.
Might be weird at your end. So we turn to regression discontinuity, which is my second favorite of these. Do you want to explain a little bit about this one and why we might want to use it?
Yeah, and once again, I think I always kind of see it as a continuum of like, well, when did I stop using the last one? And I think one of the most important assumptions with both stratification and propensity weighting that I mentioned is that like none of the probabilities on here is completely zero. Like everyone has to have kind of like some chance of having been in the treatment group, or there are like some cells, if we go back to the stratification example, where I have no treatment observations or no control, so I can't find that average effect and make the comparison. So that's kind of like the balance of like, I really, really need that overlap to make either stratification or propensity weighting. Now, regression discontinuity is helpful when I don't have that, and when my policies explicitly prevented me from having that. And I think one kind of like cool thing to me about this approach is this is actually a situation that comes up so much in all walks of life. In industry, like we'll often think about customer segmentations of like probably make a cut of like your high value customer if you're above this model score or spent this much in the last period. In public policy, there are all sorts of examples of cases where I might say, you start school this year if you were born on this day, but not on this day, or you qualify for this government program if you make this amount of money, but not this amount. So having these like sharp cutoffs come up all the time. And there are a lot of opportunities to use this method. And essentially how this works is instead of like looking for overlap across that entire population to get the complete average treatment effect, with regression discontinuity, we can only look for kind of a local effect that occurs right for the value where that cutoff lies. Because what we're doing is we can essentially fit a model of the relationship between what they call the running variable, which is the variable that's used for the cutoff, and the outcome of interest for the control population up until the cutoff, that it similarly fit a model for the running variable versus the outcome for the treated population. And then we can score both of those models at the exact point of that cutoff and compare their relative values. And that tells us that the treatment effect, not for the whole population, but at least right at that boundary. And in true to form, I guess I'll just kind of illustrate with another quick example here. One kind of example I give for this in the post is kind of in a marketing context of maybe I'm trying to re-engage customers that haven't spent with me for a while. So I send a coupon to everyone that hasn't spent in the last 90 days. And I want to see how that affects their spend in the next 6 months. It's kind of like ludicrous to say people that spent 10 days ago are similar to people that spent 200 days ago. So can't kind of compare those whole spaces. But I could zoom in and be like, well, it's kind of random whether or not the day that I decided to drop the campaign, you'd spent 85 days ago versus 95 days ago. So kind of zooming in on that narrow range around the band, it kind of feels random, even though it's not completely. So then I can kind of fit my model for future spend versus days since last spend for kind of like both groups, compare their outcomes, and try to get that effect, at least for customers that haven't spent around the range of 3 months.
My sort of go-to example with some of the threats to the validity of this approach is to do with grades. And so at Toronto, if you get 89%, then you get a B plus, and if you get 80, then you get an A minus. And so to avoid the sort of headache of getting emails from students who got 79, a lot of professors, well, I don't know, some professors just change all the 79s to 80. And this then is going to, if we wanted to do regression discontinuity, we might want to look at exactly and compare those 79s with those 80s, but that then sort of undermines some of the basis of your claims, your ability to make claims. Are there any sort of other threats to validity of using regression discontinuity that sort of keep you up at night?
So I think the two major issues that you see a lot with this type of method, first is that sense of gameability, like you mentioned, of like, it's not entirely like random always. Like if the cutoff is known to the individuals being treated or even their professors, like that can bias kind of which side of the line that person ends up on and really defeat some of the like randomness that we're trying to exploit. The other main issue is in the specification of the models that we're trying to fit on both sides of itself. As we know, I mean, at least with kind of regression models and particularly polynomial regression models, they're not known for being particularly valid right at their tails where they're extrapolating the most. And kind of by definition of this technique, you're trying to score a model right at kind of the furthest periphery of its ability to predict things, which is a little bit scary. And there are, in fact, a lot of examples in the real world of this going fairly significantly wrong. If you want a good collection of them, Andrew Gilman on his blog from Columbia is always very vocal in calling them out. I think one example that he showed not too long ago that really sticks in my mind is he looked at, or someone had done a regression discontinuity to look at the vote margin for a governor's race and lifespan of a governor. And it showed something like a narrow defeat in a governor's race took off between 5 to 10 years of someone's life as the result of their study, which I think definitely sort of shows that there's a place for kind of common sense also in these results, not just taking things at face value, or would definitely be pretty scary to get into politics.
Yeah, sorry, I'm not meant to laugh, but that was very funny. And so the point here is, so in the illustration that we're looking at here, you have linear curves, and the point here is if we made them a little bit wiggly, then we may find if the green one wiggled down at its rightmost point and the blue one wiggled up at its leftmost point. This is the type of scientific knowledge that we do at Toronto. Then we might have a larger estimate than if we had your linear lines. And I was watching the Michelrath videos. Have you gone through statistical rethinking?
Yeah.
Yeah, so I was watching the Michelrath videos last night, and he was sort of talking about the wiggliness of the tails, and it's very relevant.
Definitely.
And so we move to my favorite, difference and differences. So what's the basic idea here, and why should we always use it? No, I'm just kidding. When might we?
Fair enough. Gotta make the pitch for this one now, right? So all of these methods up until this point have really been obsessed with trying to like get as close to like super like similar, like before action treatment would have been identically the same populations as possible. Diff and diff is kind of humble enough to recognize that often isn't going to work out for us. So instead of like simply exploiting kind of like variation in assignment, it also brings in this notion of time and kind of like allows you to control for more kind of fixed effects and internal characteristics than you maybe have like data and ability to control for by kind of adjusting each observation, both for its like own behavior before treatment. So essentially kind of how this method works, and the example I give in the post is if I wanted to like look at traffic to a store based on whether or not it had remodeled, probably more expensive than I actually want to think about to go ahead and randomly remodel a bunch of stores, just like do my own little experiment. But what I could do is I could look at a set of stores that did remodel and those that didn't, and compare their pre and post behavior. And the name's kind of funny, but where it actually comes from is it's like literally telling you heuristically what you do. You take the difference between the post-action and the pre-action for the treatment, the difference between the post-action and the pre-action for the control, and then you take the difference in those differences to find the effect. And that sounds just like a pretty silly trivial arithmetic problem, but if you're kind of interested in the finer details, it's typically implemented as a fixed effects regression. But essentially, like what it is doing graphically is it's making the assumption that but for the treatment, but for whatever policy was implemented, these two groups would have had parallel trends. So even though my treatment and control levels aren't the same before, so you can't say that these populations, these observations were the same before treatment, we assume they have similar trajectories. So had there not been a treatment, I would expect my treatment to follow a similar trajectory to the control, be more like this dashed line. So anything incremental above and beyond the dashed line, we kind of can assume is the effect of the treatment. But kind of conversely, because of that, really believing that parallel trends assumption is true is really, really critical to the validity of this method, as is kind of ensuring that there isn't spillover between the two groups and that the effect of the treatment can't somehow like also influence the control population, which is something especially when you think about like social networks. I know it's something they worry about a ton in their experimentation because super hard to ever just have one effect on anything.
Yeah, my wife did a diff and diff with the hurricane Maria that went through Puerto Rico, looking at sort of a migration from Puerto Rico using Facebook data. You used to be able to grab their data and the effect of that. Yeah, I think we largely talked about all of the assumptions that we were mostly checking, that the crossovers, the spillovers, parallel trends. Oh, there we go. Monica's added in the link into the chat. Yeah, was there anything else you wanted to talk about diff and diff? Or?
Well, the one One thing I'll say about parallel trends, I guess if I could just say one more thing, like carrying on the example, that I think like, well, a couple more things. It's like a little bit more kind of pernicious and sneaky about it is I think one way that's like less intuitive where that parallel trends assumption can be violated is cases where like the tail is wagging the dog proverbially, or more specifically, the treatment is caused by an anticipated outcome instead of the outcome being caused by the treatment. So the example of that I give in the blog is like, you might choose to remodel a store because you're expecting more traffic there and you know it needs to expand. And at that point, like the counterfactual would actually be a dashed line kind of going up, 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 up on its own. So using this method would kind of violate that assumption. Oh, sorry, go ahead.
No, not at all. Sorry. You go. Sorry.
Oh, I was going to say, however, on the flip side, the positive note is diff and diff is probably, I mean, all of these methods have a ton of variance that kind of at different costs do relax some of these assumptions. And diff and diff is definitely one with a ton of variance that help you like utilize treatments occurring over different time periods, synthetic controls that maybe like can make a control that like on average meets this assumption, even if you have many individuals that maybe don't, through weight averaging. Or there's also a package from Google called Causal Impact that is uses a Bayesian time series approach to do a similar technique, but allows you to also incorporate more seasonality and time series components that you might see and associate more with like URIMA methods or something, which kind of let you think, well, maybe my trends aren't parallel, but kind of like the volatility has some sort of known relationship. So even though the assumptions are kind of restrictive, a lot of great variance on this method in particular if you really want it again.
Just a quick clarification from Lorena. What was the package name, the Google package that you were mentioning?
I believe it's Causal Impact.
Oh,
yeah,
cool.
Causal Impact.
I think one of the things that I love about the diff and diff is that essentially what it boils down to is just that you've just got to think really hard about your data, and it can be hard to get students, like you can't say, just go and think really hard about your data and then come back to me in a week. As you give them diff and diff, you don't have to have done too much quantitative training, because ultimately you could just do it with OLS really. And then they can come back to you in a week, and because of diff and diff, they've had to think really hard about their data, and I sort of like that a lot. We'll close this section just with one last question, and it's somewhat unfair because you don't actually really go into instrumental variables in the post other than to sort of mention them in passing. But did you have anything that you wanted to talk about instrumental variables?
No, I'm glad you bring that up because I almost went there, but then I kind of chose not to in the post, largely because I think those are, and this is probably a terrible reason, but I think those are actually best explained with DAGs. And I didn't want to kind of like go into the whole like drifted acyclic graph route, but I do like kind of at a high level, what instrumental variables are is very, like you can almost think of regression discontinuity as like a very, very, very trivial case of that. But kind of at a high level, the idea is I want to find some third thing that affects, like some variable that can affect my treatment assignment, but doesn't affect the outcome except through the treatment assignment, which sounds like a lot of like weird talking around. But I think kind of one of the most classic examples of that is if you have a treatment and an outcome that are very like endogenous that you can't separate. For example, like kind of the classic example is asking, does crowd size of a political protest affect whether or not like politicians listen to it or not? But you might say, you can't actually just like throw crowd size into a regression because, you know, I mean, there's a correlation between an issue that's more important is going to draw more people and an issue that's more important is maybe also more likely to get action. So those two things are kind of hopelessly confounded. But, and this has almost become so kind of a cliche in the like parts of econ Twitter that talk about causal inference a lot, that it's kind of a joke. But people might use something in that case like rainfall as an instrument that is highly correlated with crowd size because people aren't going to like show up when it's raining, but doesn't like directly influence how much over the long term politicians are going to listen to an argument. So I think like that's kind of the general premise, is like finding some third variable that's also once again kind of like inserting that randomness into the treatment where otherwise that randomness wasn't there. And tying that to regression discontinuity, that's just kind of like our cutoff, and the kind of randomness of exactly where you were on that side of the cutoff is kind of serving that same function.
Yeah, the rainfall certainly another one of those bingo card entries, isn't it? And just for folks that are not as familiar, so a DAG it's essentially what in the 90s we used to call flowcharts. So you put out your variables. So we might have political participation, we might have rainfall, and we might have I think it was issue salience or something like that. And then we draw arrows between those to sort of identify, well, what affects what. And so that's the idea there. Very popular these days through, I think, popularized by Pearl, right? Would you agree with that?
Yeah, definitely, or at least he's by far, I think, the most vocal advocate of them.
And for those of you playing along, difference between version 1 of statistical rethinking and version 2 is largely the inclusion of DAGs. Before we move on to this career sort of section of the talk, was there anything else that you wanted to say about causal inference more generally? Did you have to teach yourself all of this, or did you cover this at UNC?
So I was lucky enough to take one econometrics class kind of for fun, and we talked largely in there about diff and diff and then more like panel data style methods. Mostly the rest of this was all things that I kind of just like learned and started digging into. I think like that course really just like whet my appetite for thinking like, wow, there's so much value in found data. And then especially when I got out into industry and we had like so many problems and so much historical data lying around, I just became really passionate about this specific area. I think though, if there is like, I think like have hopefully given a good like kind of advertisement, if any, for lack of a better word, for some of these methods to date. But I think there is like, if I think I would be remiss in like ending the talk without talking at all about like the cautions of these approaches, in that like I think probably more than almost any area of like all areas of statistics to do them well require a lot of like domain expertise and domain understanding. But as you pointed out with diff and diff, I think that's even so much more true with this set of methods, because none of the assumptions are really things that we can test analytically. It's not like if I'm doing a regression, I can tell you how to like make a QQ plot, make a residual plot, calculate Cook's D, everything you'll find in like a regression 101 textbook. But a lot of the assumptions here, thinking about parallel trends, thinking about compounding, a lot of them really require like super intimate understandings of our problems, and can be like really easy to trick ourselves, and even really easy to actually insert more biases and control for things that cause confounding instead of resolving them. So I think that's just kind of like a call to action of like, I think it's a super exciting space and it's definitely worth exploring. But I also think there are methods that, not unlike all statistical methods, are worth really, really understanding deeply when you go to apply them, and understanding all the nuts and bolts and really interrogating to what extent assumptions are true. And along with that, I will mention there's some awesome tools to do that. There's a lot of work here. Like we think about, in statistics, like traditional like confidence intervals that kind of like measure statistical uncertainty. But there's also a lot of great work in causal inference, both around simulation and sensitivity analysis, to help us kind of gauge the uncertainty and put kind of like bounds around like what happened, like how badly can I break my assumptions and stuff might still kind of work out for me. So definitely a lot of like cool literature there that it's worth looking into if you're really trying to make meaningful decisions with these.
Yeah, thank you so much. Sorry, the baby is going to be crying in the background. I'm not sure if you can hear that. So, yeah, I mean, I can't agree with this any more strongly than, but it's just wonderful to hear you say it. So we might like to turn to sort of the third aspect, because I'm aware you've only got half an hour left, which is sort of career advice and things like this. I only have a handful of questions with this. So if folks want to start thinking about their own questions for any parts of your talk, but especially about this, then please put it into the chat, or you can just raise your hand and I'll call on you when we're done. So, you know, folks see all the cool things that you're doing. They're still in school, and they decide, you know, they want to get paid to do all this. Do you have any sort of high-level advice about getting into this sort of field?
Yeah, definitely. I think the really good news is there are almost countless different ways that you can get into the field. You know, I mean, I think almost any company now really recognizes the importance of data, and whether or not you come in with a title of like business analyst, business intelligence engineer, data analyst, data scientist, like I'm sure 20 other things I'm not thinking of. I think the things that's really like, I think this causal inference is a really good example of, is like these methods just kind of exist out there in the wild. Some are from econ, some are from epi, they're kind of from all over the place. And so I think no matter like how you start your career, you'll always have a set of business problems people want you to ask, and hopefully some sort of analytical toolbox. And I think I really, for me, kind of see my job is just always finding ways to like marry those two. And it works spending time like understanding more and more what those business problems are, also building out just like all the possible tools to like find more situations of serendipity. So I think like, as I trace that back to kind of like students and career advice, I think kind of the salient point is like, especially early in your career, I think like definitely take risks, explore, like try to learn like a lot of breadth of things to build up that mental index so you can really kind of be ready to mobilize and kind of like go deep and apply something when you see a problem out there in the wild that maybe has some nice metaphor.
Yeah, I love that. You're sort of saying at the start how when you're at work, you don't get told, well, this is a regression discontinuity problem. You just have to sort of figure it out. I do apologize to the baby, so come say hi to Emily.
Hello.
And so on the other end, so I think most people are probably familiar with applying to jobs. But from the other side, so when you're hiring, when you're evaluating the folks that have applied, what are the sort of things that you're looking for? Are you looking at cover letters, GitHub repos, websites, grades? Is there anything that really stands out for you? And obviously this is, you know, I am asking you, but more generally sort of your thoughts about it rather than specifics.
Yeah, definitely. And without, I think, talking too much about my company's hiring process, I'll answer that from the perspective of like, if I were starting a startup tomorrow, what would I be looking for? And I do really think the most important signal to try to give an employer is that willingness and ability to keep learning, because whether it's code stuff like R versus Python versus Spark versus who knows what's coming down the road, whether it's methods, we are in such a like fast moving world that I think just the ability to kind of like keep up and the willingness and the wanting to keep learning is super important. Fortunately, I think there are like a ton of ways to show that. I do think learning in public and working in public is a fantastic way to do that. So if you want to start a blog, if you want to put stuff on a GitHub repo, if you want to come join the really fun and friendly like communities, even on Twitter or many other places, I'm sure, I mostly spend my time on Twitter, but that like are just kind of in a constant conversation about stats and R and Preppy and econ and whatever domain interests you. I think just getting involved both builds your network. It helps you figure out better what it is you actually want to do because you get to learn about what so many other people are doing. And it shows that kind of just like kind of willingness to really lean in and learn. And just the last point I'll make on that, I feel like when I was a student, I was like, but what would I put online? Like, what do I know that other people don't know? And just as a sample size of n equals 1 with me, I think like objectively, if you think about this blog post that brought me here today, does not have one novel idea for me. This is like all like stuff that's existed out there in the wild for a long time, but sometimes just like pulling things together and kind of explaining them in a new way to a new audience can still like be valuable. And of course, students these days are getting to learn all sorts of things that probably didn't even exist when a lot of us were in school. That, I mean, definitely know that you have something to bring to the table, and it'll definitely be a very welcome part of the conversation.
Yeah, I try to force the students to make websites and then add blog posts, and I moved away from that this term, but I think listening to you, I think that I should definitely go back to forcing them to do this.
Oh, now
do you have any other advice? Oh, sorry.
Oh, I just said now you're blaming me.
Yeah, that's right. This person in the industry said to do it. They'll believe you. Do you have any other thoughts around how we could be better as teachers for preparing students for the workforce? I mean, many of us have never even like worked in data science or broadly defined jobs. Are there things that we could be doing and changing that would be useful?
Well, I have two incredibly like contradictory thoughts there, so I will say them both, and you can do what you want with them. I think first, it is kind of interesting when I think about my background. Both of my all of my undergraduate studies were very, very much on the theoretical side. UNC was more of a like theory heavy stats department, but then I apparently wasn't doing enough proofs because I went and signed up for a math major too. But there was a point where, when I was first on the job market, where I was like, oh, I should have spent my time like learning R. I should have spent my time like, you know, doing these things that it says in the job requirements. Overall, I think I'm super glad that, and I think it's like a really good thing to in school, like really learn all the theory. You were asking, for example, like how I got into all this causal inference stuff. And I mean, I think it has been a helpful background, and that I like totally feel super comfortable like picking up a random book or random paper and having focused more on kind of like principles versus applications. I think kind of builds that good platform for just like continual learning of kind of whatever really sparks your interest. The flip side of that I think is probably one of the biggest gaps as students come into industry is not having touched real world data. Because I think like you don't realize until kind of like you leave school that one of the biggest like jokes that all statistics departments tell is like, assume you have this matrix X, that then we can put in like the regression formula. Because getting that matrix X is probably one of like the hardest things you will ever do. Kind of as this like really all causal inference says is kind of like ways to make up for the fact that you don't have the data that you want because you don't have that experiment you wanted. But there are also like technical glitches that you don't have the data you want. There's also like data warehouse loading errors that you don't have the data you want. There's also lack of metadata that you sometimes don't have the data you want. And I think like it's very contradictory because I think like theory is so important, and I would never say do less theory, but I think also kind of understanding the gap between statistical challenges and actual where does like what happens when you like try to shove real world statistics like data into statistics is kind of like an interesting middle ground.
Yeah, occasionally I try to do real world data sets in my classes, and occasionally I get angry emails from the undergraduates I won't name the fields, but you know, from certain fields, and they say, you know, in field X, we get given clean data set, we get given the data. Why don't you do that? You know, you're horrible. And I've just filed those emails away for in 3 to 5 years when they sort of hopefully email back and apologize after they get jobs and they realize that. Anyway, we'll see. We've got about 20 minutes. Did folks have any questions that they wanted to ask Emily, please? You can either just raise your hand and I'll call on you, or you can add your name to the chat. Please just briefly introduce yourself so that Emily has some idea as to whom she's talking to. I'll just start with Faria, who's one of the co-organizers of this group, and then move on to some folks who are in the class that I'm teaching this term, unless other folks jump in the chat. But Faria, did you have anything to start with?
Yeah. Thank you so much for your talk, Emily. I don't have a question, but I want to thank you for the insights that you gave about, just making like whether to publicly post your work or